going to listen to the last talk of this session, which is also the last talk for today, but don't leave after, because we have a discussion from Rohan, who's going to talk to us about Bayesian modeling, this time with Comrade. Thank you.
So we have heard a lot about ill-posed problems, a lot about Bayesian from Thorsten. So I don't have to introduce a lot why it's important and not. But I would like to emphasize that I'm a big fan of quantifying errors, and that's why we should use Bayesian methods. Other than that, I don't like so much approximation techniques. So let's just try to put a big jackhammer and just try to fit everything we can. So what are we going to do? We are going to do a full Stokes, meaning all Stokes parameters modeling and also imaging with Comrade. So Comrade is basically a very composable and modular framework of radio emission. So meaning we can think of it like Lego blocks. We can make models anything we like. If you may want to make an ellipse, just put a ring and put ellipse to it. If you want to put a different optimizer, just plug in different optimizers from any Julia library. If you want to use a different sampler, use a different sampler. So it's more like putting all Lego blocks together. So this is being developed by Paul Dida, who is at BHI Harvard. And this is now a very well documented software, which has a link of GitHub here, and also has a JOS paper, so you can check it out. I'm more of a big fan of a user of this software, and I'm going to show what kind of use case I like to do with this software. So first of all, we have the VLBI data, which is, as everyone knows, is ill-post sparse data coverage in the Fourier domain. It is corrupted in terms of atmosphere, instrumental effects, everything. And other than that, I think Kazu also mentioned that some kind of interferometers, they are mixed pole interferometers, meaning that some arrays record in circular polarization basis and some other records in linear polarization basis. So we need methods which can really tackle this mixed kind of instruments. So this is the data at hand, and we are going to see what kind of model we can fit to this data and get out uncertainty quantification of every single thing that should be represented. So this is a lot of equations. Just for the sake of an example, what I'm going to do is I'm going to fit M rings, which are basically just cosines in angular direction, and then some radius to it and some width to it. And I'm going to put this M rings in all Stokes parameters, I, Q, U, V. And then, if required, we can also have some kind of ellipticity and position angle to it. So this is the modeling in the sky part of the thing. And then we also have things like gains, D terms, and feed rotation. So feed rotation is not really a model parameter. Every single model parameter is labeled in red. So gains are at each timestamp that we have the data for, and they are different for each of the stations. And then we also have D terms, which is specific to each station but constant for an observation. Feed rotation is basically just different kinds of mount types we have for any kind of telescope that we use. So this is a priori applied in some kind of data like EST. Sometimes you have to apply during the modeling procedure. So other than that, we can also have one more matrix in this Jones, which is the basis transformation. So since I talked about different mixed pole thing, we can just apply another matrix to convert from linear to a circular thing. So then we can just fit any mixed pole interferometer. So this is important. Bayes is an important thing because Bayes doesn't say that we don't have any prior assumptions. It just makes us be upfront about it. And so I think it's important to talk about what our prior assumptions are. In this case, where I'm fitting an M ring for all the Stokes parameters, most of the model parameters are uniformly distributed. The gains are normally distributed. And this usually comes from what kind of data we have. So we already know how much should be the gain width for that distribution. And other than that, we also have D terms, which are also normally distributed in the complex domain. So more or less, almost not too conservative priors. We just give a broad range and everything mostly uniformly distributed. And just a side point, which I have not mentioned till now, the M rings can be of any order that we select. So for Stokes, we can select like 3 order of cosines, or Q, the polarization we can select like 4 or 5. So we have to select what kind of order of cosines we are using. And so this is modeling because we are having some kind of prior assumption of what kind of thing we want to fit to the data and see how well it can fit to the data. We can select what kind of model performs the best based on Bayesian evidence, or we can also directly do an assumption-based approach, which is just imaging. So now that we have the prior and our model, let's just design our posterior that we want to sample. And that is basically just given by this equation where we have the Jones matrices of the gains, the d terms, the field rotation, and then the row of M is just the model visibilities that we have, which then we corrupt with this Jones matrices. And that's how we get this model corrupted visibilities, which then we compare with the observed visibilities. And then that's how we say that, okay, the data is now normally distributed with some noise to it, and that forms our likelihood. If you multiply it with the priors that we just designed, that we get the posterior. This is, I think, everyone knows this. Just a side note, as I've mentioned before, here, as I see with this T, that's just the basis transformation if you have a mixed polarization interferometer, and which makes our life easier. And so, important point about sampling. So till now we have heard about variational inference, geometric variational inference, and a big problem of these methods, according to me, is unimodality. It assumes unimodality, and so when we have highly multimodal posteriors and we want to sample it outright, then we need some kind of samplers which are very fancy and can explore all the modes. And as we have already seen in some of the papers of EHD, that the data can actually have 2 different modes or 3 different modes. So this is one of the sampler which I really like. It's an extremely state-of-the-art parallel tempering sampler, which you can just run multiple chains in and just use multi-thread and distribute it over different MPI machines. And so since this is a modeling thing, there are less number of degrees of freedom, so you can just use this sampler, which works very well with less number of dimensions. And so on my machine, this runs for less than 2 hours for this order of magnitude of 100 dimensions. And this is the result I get for the 2017 Hamaker. So here we see the EHT image that was released. And this is what we get for the M ring that we just fit in all Stokes parameters. As we see, the chi-squares are a bit high. That's expected because this is a model that we have assumed that can fit the data. And so it's not exactly fitting all the different intricacies of the image. But it's still pretty great fit. Good thing is that because of this, we have error bars on everything. We have error bars on gains, we have error bars on the D terms, and the gains are kind of as expected, and the D terms are also very small, close to less than 10%. So which is great. So this actually fits very well the 2017 M87 data. The good thing is that since this is already designed now, modeling works very well when we have very, very less data. And this is true for SAG. So if you want to do a modeling of SAG, an instantaneous one, we can use this kind of modeling thing to fit the snapshots of SAG and get a snapshot movie out of it. So I'm going to go quickly over this. In terms of imaging, the only thing that changes is the image model. There's a lot of equations here, I know. But what it basically does is that we want to have a positive image. The image, we assume a total flux to it because that can be adjusted by gains. And then we want the image to have some correlations to nearby pixels. And so this is designed by some Gaussian Markov random field, where the terms are resembling for RML total squared variation and L2. And the hyperparameter is actually correlation line, where we usually set through the resolution of the data, which is up to the beam size or nominal resolution. And then the dispersion of the field is something that we fit. And so we are actually fitting for the total squared variation or L2. So here we apply this kind of prior to the Stokes I and the total polarization. And then alpha can be thought as EVPAs of the image. And then beta can be thought as circular polarization, the degree of it. And so this is the image model, and the priors that we use are also uniformly distributed for alpha and beta, and I is as Gaussian Markov random field, same for P. And then if we look at the image, which also looks very similar to the published 2017 M87 image. So, and this actually sampling takes less than 2 or 3 hours just on my normal 8-core laptop. So it looks pretty great, and I'm a big fan of this method. But how does it scale? Yes, okay. This is my last slide. Yeah. Okay, very quickly. So how does it scale? We can fit things like VLBI datasets. We can also scale up to the space VLBI, like radio astronaut. And so good thing is that we can get features that are have more SNR and figure out what are the more SNR features of the images. To be developed, this is up to, we can scale this to GPU and make it super fast. This is to be done yet. And then we still need to do this in multi-frequency and time domain. Yeah, that's all.